Okay. All right. Good morning or good afternoon, depending on where you are. And I'm Yuding. I'm a faculty member of Georgia Tech, and I'm running this data science for wind energy webinar series and discussion series on a monthly basis. So welcome to this series today. And today we are very pleased to have Mario Di Florio and a postdoc right now at Unreal. But Mario had actually applied math training background. So he worked on machine learning from mathematical point of view for a very long while, and recently come to apply those kind of concept method to wind turbine maintenance and gearbox diagnosis and so forth. That's exactly the type of combination we look forward to seeing. And data science and demand science kind of they meet with each other, right? So without further ado, and the floor, well, I should say the platform is yours, and Mario.
Thank you so much, you. Let me share my screen. Can you guys see my screen?
Yes.
Yes.
Can you make it full screen? Yeah, great.
Perfect. Thank you so much for the introduction, you. Thanks for everyone to join this webinar. And today I'm going to show you our presentation on gearbox bearing crack growth prognostics and uncertainty quantification using physics-informed machine learning. So during this presentation, I'm going to show you, of course, our motivation that led us to do this work, the kind of physics-informed machine learning frameworks that we are using, which is not a classical physics-informed neural network, but as we'll see, it will add some new features to tackle this kind of problems. And the application will be, of course, on wind turbine gearbox bearing, prediction of the remaining useful life. And then we'll throw our conclusions. So the motivation that led us to start to work on this field is that wind turbine gearbox failure or reliability challenges will, of course, leading to an increasing of operations and maintenance costs. So we will need to monitor to project damage progression and perhaps optimize operational and maintenance. We aim to do this by leveraging both the benefits from both the observational data and physics domain knowledge that we have of this kind of systems by using physics-informed machine learning. So for who is not familiar with the physics-informed machine learning, I'll try to do here a very brief overview. And as we know, basically, for a certain physical phenomena, we can have two different ingredients for modeling its behavior. One is observational data. But as we know, observational data, many times they can be noisy, they can be sparse, they can be difficult to collect or even impossible to collect many times. On the other side, we have physics-based models. Many times modeled by differential equations for our cases. And as we know, as long as they can be even accurate many times, other times they can be not precise and they can be based on certain mathematical assumptions. So the concept of physics-informed neural networks is using both of these ingredients, so observational data and residual of the differential equations, to train our neural network. To give a little example, here we have a damped harmonic oscillator. Let's see what happens in case we use traditional machine learning, where we only have a data-driven training. Let's consider these spring mass systems as example, where we have only few observational data, which are represented by these yellow dots. So we don't have observational data through the whole time domain of this physical system. In our data-driven training, our goal is to doing a linear or non-linear mapping from time to the position of this mass spring. In a classical neural network, so our objective is to minimize the loss function, which is in this case it's made basically by the difference of the representation of our neural network and our observational data, to find by finding the optimal set of neural network parameters. As we can see here from this animation, as long as we have observational data, the neural network can do a good fitting in the data. But after we lose information, of course, there's no more information for the training, and many times the neural network can fail in this task, especially if we don't have a large data set. Like in this case, we have just a few points for a certain amount of time. So the concept of physics for machine learning is giving a more information of the system to be able to perform a prediction, forecasting, or parameter estimation, or whatever we need to perform. So how does it work? In the loss function of the neural network, we don't only have the loss on the data, but we also have the loss on the physics, which is basically the residual of the differential equations. In this case, for example, we have knowledge of the physics of the system, of the damped harmonic oscillator, which is basically this second order ordinary differential equation subject to boundary conditions. So here our objective in the loss function is made by these two part of losses that we want to minimize by finding the optimal set of neural network parameters that minimize both of these loss in the same moment. As we can see here from the animation, now, even having only a few observational data, we can we can understand the future behavior of the system thanks to the information brought by the differential equations. So a classic physics-informed neural networks has a schematic like this figure that we have in this slide. This is a framework developed in 2017 by Raisi, Perdigaris, and Karnedakis from Brown University. Since then, it brought a lot of attention in the world of machine learning, in the world of applied mathematics, and in simulations in general. It works very great for forward models, for inverse problems, but of course, as everything, it has its limitations. I believe its main limitations are the fact. The first one is the fact that we need to use gradient-based methods or backpropagation to find the optimal set of neural network parameters that will minimize the representation of our neural network, and so minimizing the residual of the differential equations. But using the the backpropagation will lead to certain problems. It's computationally expensive, so many times it cannot be used for real-time simulations. The complexity of the network can cause divergence, and for this architecture, linear problems will be treated as nonlinear problems as well. Another limitation is that initial and boundary conditions of the differential equations are included in the loss function. That means that in the training process, we also need to learn the solution of the differential equations on the boundary or initial conditions. This will be computationally expensive, especially for partial differential equations, and this will lead to presence of competing objectives in the loss function, which will cause gradient pathologies, causing the training failure in learning differential equation constraint, and also it brings an additional introduction of parameters, of hyperparameters of the neural network. So the work that we've been done since 2020, when I started my PhD at the University of Arizona, it was basically trying to avoid or at least mitigate this limitation, particularly for dynamical system. So we had the two features, modified two features of this classic PINS framework. The first one is using a single layer forward neural network where the input weights and bias are not part of the training. Actually, they are previously randomized, and the only unknown parameters of the neural network that needs to be computed are the output weights. This can be computed via least square algorithm. This was firstly proposed in the field of machine learning by Wang in 2006, and it was called extreme learning machine. Actually, this kind of neural network is way older. It's probably from 1958, the Rosenblatt perceptron. It has the same concept. And the convergence here is guaranteed for any input weights and bias that are randomly chosen from any continuous probability distribution. So in this case, we don't have a deep neural network. We don't need to do backpropagation, just a single neural network using least square to find the output weights of parameters. The second feature that we use is the theory of functional connections, which is a mathematical framework developed by Daniele Mortari in 2017 from University of Texas A&M University. And basically this theory of functional connection, TFC, is a functional interpolation technique that is based on a certain constraint expression, which are mathematical functions that can express all the possible functions satisfying a set of constraints. So basically, this constraint expression provides an approximation of the solution of our differential equation, which is made by the sum of two parts. The first that we can see here is g of x, which is a free chosen function that must exist on the constraints. And the second one is an expression where the constraints of the differential equation are embedded. So it doesn't matter what kind of free chosen function g of x, this constraint expression will always analytically satisfy initially boundary conditions, as we can see here in this animation on the right. So by using both a single layer neural network and theory of functional connections, we developed this XTFC framework, which mitigate the limitation of classical pins that we showed before. One, because we don't use backpropagation anymore, but least square. And the second is because initially boundary conditions will be analytically satisfied, so we don't need to do any training to learn the solution on this part of the domains of our problems. Then we also advanced this framework. We advanced for different tasks like parameter estimation, missing term identification of physics discovery, but also to provide an uncertainty quantification. And this is a framework in Monte Carlo XTFC, because we use a Monte Carlo ensemble to perform a bunch of different simulation and understanding how can we quantify different sources of uncertainty. Here we have a simple pedagogical example using these simple differential equations, where the goal was estimating the parameter k, having some limited noisy and sparse data, observational data. As we can see here, in the first column, we have the first column top plot, we have the quantification of aleatoric uncertainty, which is a kind of uncertainty coming from the observational data that we have, so it's not reducible. Second plot, we have epistemic uncertainty, which is a source of uncertainty that comes from the model itself, from the algorithm and the framework that we are using to compute our solution. Finally, we have the sum of them, which is considered total uncertainty. In this table here, we can see some difference in results compared with the ensemble pins. So it's basically using classical pins in an ensemble fashion, running 10 simulations. In this case, we were probably using 50 or 100 Monte Carlo simulations. We can do it because it's very fast. Indeed, we can see that wall times for the different methods. XTFC is pretty faster. And here also we have a comparison with Bayesian pins, which is considered one of the state-of-the-art for physics and for machine learning that can perform uncertainty quantification. So we used for this work of prediction of failure of bearing in wind turbines, we use this Monte Carlo XTFC, and we're gonna see here some results now. So first of all, we wanna see what are the two ingredients that we use, or that is observational data and physics models. For the first case of simulations, we use the vibration-based HI, or health index dataset, provided by some colleagues from 2020. So the plot on the left show us the calculated vibration-based HI dataset, which, as we can see, is pretty noisy, and on the right we have a photo of an example of a crack in a 2.2 megawatt wind turbine gearbox bearing. So this is the observational data that we are using. As of physics models, after a little literature research, we found three main ordinary differential equations models that would help us to model the bearing crack length. And so we have the linear elastic fracture mechanics, the heads theory, and the dislocation theory. All of these differential equations model the variation of the load cycle over the variation of the crack extension. By plotting these three models over the dataset that we have, we saw that probably the best one that will fit our case is the heads theory. So the number two is the physics model we used for our simulations. Let's see now how the framework performed under different situations. So here we have always the same dataset. In these four plots, we can see, let's say, different availability of datasets. Starting from A and going to D, we have 100% of knowledge of the dataset, so for all the time domain. Then moving down, 75%, 50%, 25%. We always kept to reducing the dataset to understand how the framework will perform by having less availability of the data. In this case, we are not performing uncertainty quantification yet. It's just a forward model. And also another parameters that we are varying for each of these four data cases is the weight of the physics that we are giving to the loss functions here. Here we can see on the top right our total loss in our neural network is given by the loss of the data plus the loss of the physics, both of them multiplied by their respective weight. So here we consider physics data always equal to 1, but we want to decrease the weight of the physics from 1 up to 0, going from 7.75, 0.5, and 0.2. And we can see here that when we have full knowledge of the data, doesn't matter too much if we decrease the weight of the physics, because we have full knowledge of the data, let's say, of this system, so we can perform a good interpolation, let's say, going through the data. While we have less data, of course, if we also reduce the knowledge of the physics, as we can see here in the plot D, we don't have a good prediction of the failure of the bearing. So of course we don't have knowledge of the data. We have less knowledge of the physics. We cannot do a good performance. But increasing the knowledge of the physics, so giving importance to the differential equation that we have, even if we don't have enough data, as we can see here, still we can perform a good approximation and a good prediction of when in how many hours the wind turbine, the gearbox bearing will reach an H index equal to 1. In our case, we consider H index equal to 1 when we reach failure. From this table on the top right, bottom right, we can see for the different data availability and different physics weight, the remaining useful life error given in hours, where we consider full data availability and physics weight equal to 1 when the error is 0. That's in that case is our benchmark, let's say. It's our truth solution. Going down, we can see that the error varies between 9 hours to up to 600 hours, where we don't have knowledge of the systems at all. For all of these systems, our computational time is in the order of milliseconds, and this lets us understand that we can use in real time, especially. So that means that we can perform prediction at each instant of the life of this bearing, and then updating it step by step while we can achieve and obtain more data in time. Here we have some results of Monte Carlo XDFC, where we don't only perform prediction of the failure of the bearing, but also quantifying the uncertainty of the results that we can have. So here we perform epistemic quantification for different data set sizes, like before, from 100 to 25%, considering the weight of the physics equal to 1, so giving all the importance to the physics. Here, so in these plots, we can show three confidence intervals with 67, 95, and 99.7% of confidence, and all these simulations are performed with 100 Monte Carlo realizations. In this bottom right table, we can see that for all the cases, we can achieve good accuracies, good performance with a range, depending, of course, of the data availability. But in the worst case, we have a range of minus 100 to minus 7 hours of reliability that we can have for the prediction. Again, this is something that can be performed step by steps and updating the results while we will collect more data in time. So the error will always be decreased in time while after we receive more data. So another case that we studied is not vibrational data, but the SCADA-based health index data. So basically, this data is obtained by TU Delft, by colleagues of us from TU Delft, and they used to obtain this HI data, they used the convolutional autoencoder that takes short rolling windows, as we can see here in the top figure, takes a short rolling windows of multivariate SCADA data and compresses each window to a single bottleneck value. After the training, this bottleneck is scaled to 0, 1, and this will be used as our new HI data. Here on the bottom, we can see 6 plots, which are the SCADA-based HI data for 6 different wind turbine gearbox bearings. And to show the possibility of using our framework also for this kind of data, we selected 2 of them. And here we have some results. Same cases as before, quantification of epistemic uncertainty while predicting the remaining useful life of these bearings. Here again, physics weight is equal to 1 on the equation loss, computing the confidence intervals for 3 different percentage of confidence using 100 Monte Carlo realization. And here we can see that for both cases, we have a forecasting confidence of about 10 days. So how we can drive our conclusions? We show how XDFC, Physics Informed Machine Learning framework, can be used to tackle this kind of problems with pretty much good accuracy and very low computational times by merging both theory of functional connections and random projection neural network techniques, and those combining both physics modeling, physics differential equation, and observational data, and performing also uncertainty quantification by using this XTFC in a Monte Carlo fashions. We applied this framework to 2 different kind of observational data, which are vibration-based health index and SCADA-based health index. We can see that there is not much difference in using this kind of both of differential this kind of observational data. And so what we want to do is trying to improving the remaining useful life accuracy and decision confidence through physics guide models and uncertainty quantification, and enabling proactive maintenance, those lowering operational maintenance cost and turbine downtime. Of course, this framework can be generalized to other rotating machinery and power conversion systems, which is probably something we're gonna aim to do for our future works. I think we're good with our slide. I thank you very much, everybody, attending these seminars. And please, if you have any question, I will be glad to try to answer.
Well, thank you very much, Mario, for the talk. And we do have quite some time left to probably have some discussion and any questions from the audience. Well, I probably can get started.
Mario,
Okay,
Mario.
go ahead. Yeah, go ahead.
Yeah, I'm thinking in a very practical way here. You have a turbine, so you are telling us, of course, that this is fast enough to implement this as a loop, no, every certain time, because even with the 100 Monte Carlo simulations, it's fairly it's fast. It's I mean, maximum. Okay, 100% data availability. It doesn't. I mean, it makes no sense. But for instance, for 50% of data availability, 5 seconds. Okay.
Yes, for 100 Monte Carlo.
Okay. Now in this loop system, okay, you are monitoring. There was a picture of the crack of the structure.
Yeah.
Okay. You have some sort of cameras to update the evolution of this crack. I mean, how in a practical way, how do you what sort of method do you use? You have a permanent camera there. How do you monitor this structural part? How do you update this length of A?
To be honest, I'm not sure about this because I'm not an experimental scientist. So I don't know exactly how this data has been collected. In this case, it's vibrational data.
Okay, but in a real application, you would, I mean, one would have to monitor this length, no? Because that's going to change, no, with time. Because it's going to go, I mean, exponentially worse, no? I mean, the more. Okay.
Exactly this noisy scattered data that we can see here in these plots.
And this length is an input for the network.
Is the input for the framework? Yes.
Okay, and if you are updating, and every loop you would update to
every loop
the state.
Yes, whenever we collected more data, this new data will be new input for the new time steps in the framework.
Exactly.
It will allow us to update the final results. We already have our final prediction from the beginning, but more often we collected more data.
Yes.
And then we can update to obtain a better precision of the final prediction.
Yes. Okay. Yes, that was my question. You're still trying to figure out this loop. This loop.
Yes. We didn't implement
Thank you, Mario.
Yet, but this is part of the future works that we'll have when we start for real cases problems.
Yes. Okay. Thank you, Mario. Yes, really interesting.
Thank you so much.
Any other questions?
Can you hear me okay?
Yeah, sure. Yes.
Yeah, sorry I joined late. I didn't have this on my calendar. I think that's a problem for me. If it's not on my calendar, I would normally ignore. So I think it's a great question for the health index data. If we look at the current chart on this slide, we go from D to C to B to A. It's kind of a reflection of the actual implementation in the field, right? In the beginning, you have a limited amount of operational data. You can only get access to that much. And then you calculate the health index, you feed to the model, get the corresponding outputs. So I think as you get more data, you do the simulation again, modeling again, you get more accurate data. That's how we see moving forward in the field, how to implement. We are looking at the partnership opportunities with the industry. So if you are from the private sector, welcome to talk to us.
Yeah, so Xiao mentioned about this calendar problem. When I was running the webinar series initially, I do have everyone's email address, so I can send the calendar invite to put this event on the calendar. But recently, the WeDoWin changed the way how they operate. And so I only can send the notification through the when they don't really allow me to handle everyone's email
Okay.
anymore.
That's
So
my
if you
problem.
don't,
I didn't register.
yeah, if you don't sign up on the Win, or if you join from outside, there's I talked to Sarah, who manages the Win platform, and she said, no, you're not gonna have everyone's email, that's for sure. So yeah, that's the reality. So
Okay.
Mara, can I ask you a question? If you don't mind, go to slide number 16.
Slide number, this one. Yes.
Yeah, yeah. Right. So in this case, you said the lambda physics equal to 0, 0.25, 0.5, and so forth. What is the value of lambda data
It's kept equal to 1.
all the time?
Yes, all the time. It was
Okay,
just,
so when the lambda physics are changing,
yeah.
your loss function value is at a different, slightly changing, because your weighting is the weight coefficient is different.
So we made this to show the meaning of using a physics informed kind of neural network. Indeed, when the lambda physics is equal to 0, we have the case of the loss it's equal just of loss of the data. So it's fully data-driven model. And that's why we want to show that in the case, look at the plot D. In the case where we have a fully data-driven training, and a very limited availability of data, we cannot perform a good prediction. But even if we don't have a lot of data, in case we have lambda physics equal to 1, fully physics informed machine learning, we can still perform it. That was just to prove the robustness and the efficiency of this kind of frameworks.
Okay.
Mentality
So your
machine
yeah,
learning.
go ahead.
No, just I won't say the mentality of this machine learning, where you can embed the physics even there where data is very scarce.
Okay. So the data fitting alone part, the first term without the physics part, you said a single layer neural network.
Yes.
So for example, if you look at the figure C, right, you have about half of the data, 50% of the data, which is the red data point. I'm pretty curious to find even with that part of the data, the prediction beyond that point actually they take that turn, right? That is the kind of defy intuition, because usually the beginning part, the 50% is pretty linearly scaled up.
Yeah.
Right, if you do the extrapolation, if there's nothing really guide them to do something, they should keep going in that kind of direction, right? Why they can really kind of, what kind of knowledge? I mean, if you have physics, I understand they kind of turn, right? But
Yeah.
here it's like without physics, if you look at the curve with zero physics weight, they still turn up.
Yeah, but because even from 0 to 50%, the data is still it's increasing anyway. If it would have been flat, then it would.
But not linearly. The first 50% data is pretty much linearly scaled up, right?
Yeah.
You don't really have that kind of if you see even 75%, they don't really see a very clear trend kind of going up in that kind of sharp turn upward. So that is a part I couldn't really.
Not sure how we can understand to that trajectory. That would be a case of it would be interesting. Thanks for the question. Actually, it would be interesting to do a Monte Carlo ensemble for the case where the physics for the physics is equal to 0, so it's fully data driven. To see, I'm pretty sure that for different realization, that solution will get a different trajectory.
So Jorge has something to say.
Yes, Professor Dean, I had this question with your comment, no? Because I'm seeing here like a previous step, like a 0 step, okay? Which is a physics model selection. Okay, do you remember when you selected between 3 models? There is a slide there. Yes, exactly. These 3 models, no? Look at these 3 curves. These talk about how this is going to rise, no, the physical, how you're going to explain, okay, how violent, so to speak, no, the purple curve is really violent at the end. I mean, it's really, wow, super. Okay,
Yeah.
and I was wondering about how, if there's a serious step where you have to include this model selection, okay, in order to generate like different stories, okay, depending on the model, different yes, acceleration, let's say, no, of the remaining life. So yes, and that was that's my question. Is it possible to include this as part of the whole simulation of the uncertainty?
You can basically in parallel you can compute the prediction using all of these three models. That's totally possible to do it. It's actually that's something that it's even we can do it for future work, even to do a comparison and understanding particularly which one would be better for both the vibrational and the SCADA-based data.
Exactly. One important point that I find is that one needs enough data or enough these points, these gray dots, okay, in order to choose the model.
Yeah.
So that's going to make us that, I mean, that we have to think first, okay, yes, you are telling us that we can operate with 25% of data, with 50% of data, okay? But before this, we need enough data, let's say 70% of data, in order to fit the proper model.
Yes.
Okay, so there is like a limit there, a specified amount of data that we need in order to properly assess the physics of the phenomenon.
Yes,
Yeah.
you're totally right about it. Indeed,
yes.
What I wanted to do for future works, it was exactly finding more accurate physics models that can model this kind of phenomena. Which literally is not, for what I saw, is not very rich in this kind of things. But we are thinking about using the same framework for different kind of physics models without using this kind of fracture mechanics, but even energy frictions maybe in the future. So totally different physics.
Yeah.
So that's a work that still needs to be done to increase the reliability of the framework using more reliable physics.
Yeah.
Thanks
Because
so much.
there is a threshold of data that we need to fit the physics model. Yeah.
Okay, Christian raised the hand. Okay, go ahead.
Yeah, thanks also from my side for a very interesting presentation. Just on that note, I was thinking, would it also be an interesting problem to optimize the weights of the data and the model? Like, do you think that would be a way to work out how
you're talking about lambda data, lambda physics?
Yes.
Actually,
so I guess it depends on
actually I will
quality of data, quality of or uncertainty in observations, uncertainty in physics-based predictions.
Exactly. I will personally always use both of them equal to 1 because so you can use the full loss. But there are many cases where probably data is too noisy, and you want the framework to perform with less bias on the data, so they can follow better just the differential equation, maybe to have a smoother solution, for example. So you to obtain a smoother solution, you reduce the weight on the data. That's something that I will think about it. I wouldn't say that I will find a way to make it an optimized way to find these the values of these weights, because I believe is more, for at least for this case, is more a user decision on how you want your solution to look like. I don't know if it's clear what I'm meaning. It's very problem dependent.
Yeah.
I will personally
use
both of them equal to 1.
Dr. Bian?
Yeah, this is great talk. I guess you focus on finding this average behavior over time. So you want to find this kind of solid curvature. But in the that's really good. But in the reliability analysis and for O&M, I guess finding the probability that this crack size increase some resistance level is really important. So for that, I guess you need to have some probabilistic prediction. And that I think is related to how the noise varies over time. So here noise level is small in the beginning, but it increases over time. So I wonder whether your approach can be extended to incorporate this kind of heterogeneous noise in the end can lead to some kind of probabilistic forecasting for the RUL.
Yeah, well, here we show in these slides just the epistemic quantification. In our paper that is printing now, we also show the aleatoric uncertainty, which of course it will increase in time because as you just said, the noise of the data will increase, and that's an uncertainty that cannot be reduced.
Mm-hmm.
So here we show just the epistemic uncertainty just to prove how robust and reliable can be the framework itself for the prediction. Not as much for the real case prediction, but just to show how we can reduce, at least for the epistemic uncertainty, the confidence interval. Indeed,
Okay.
you can see that going from D to A, we can always restrict it. It's called getting thinner and thinner, the confidence interval. Mhm. But yes, if we have to base only on the observational data, which is very noise, of course, the uncertainty will be very big.
Mm-hmm. Another question I have is, so when you use this physics-based model, I think that's my question is related to the previous question. So if you have a kind of more complex model, so it's not just one equation, but you have like a set of equations, then how can you incorporate this kind of complex model into this framework?
Oh, it's not a problem at all. We applied many times this framework for dynamical system with even hundreds differential equations. You just you will have different losses. Each loss is a residual of the differential equation, and you perform it in the same way. It can be a linear or even non-linear systems of differential equation. It doesn't matter. And of course, you will have different prediction for the different solution of the differential equations. Yeah.
Inside the model, so inside this kind of complex physics-based model, you should have some kind of parameters to estimate, right?
Excuse me, can you say it again?
So in your model, if you go to page 7, the physics-based model, it's not. So there is this three physics-based model, A naught and A, that includes A naught and AF.
You're talking about this one?
Yeah. Then you need to estimate this A naught and AF in that engineering model, right?
Oh, if you want to estimate A0 and AF.
Right.
Yeah, you can do it by you can perform a parameter estimation here. Since you have data, you can retrieve the values of A0 and AF. In these cases, this is a particular case because we don't have a good reliability, both or neither the physics model, as I said before, we cannot totally rely on these physics models because I believe they are pretty much too much simple, and not even on the data because they are very noisy and so in this case we performed a forward model by using both physics and data.
Right.
In most cases, with the same ingredients now, we could even perform inverse problem. So basically, we have the data of HI, which in this case is A. We have the data of N, which is our time. And so we can easily do a parameter estimation of both of these. That's I didn't perform this because it was not our task, because these are parameters that are user selected. In this case, A0 we consider to be 0.05 because it's the value where we consider the bearing to start to achieving failure. And AF is the final, where for us the HI equal to 1 is the moment in which the bearing achieve total failure, basically. So these are
Oh, so
the
in
user
this case,
selected,
this
but
A0 and AF are given.
yes,
Okay.
yes, are given, are user
Okay.
selected. But mathematically wise, for the from the framework point of view, it's possible to do
Yes.
parameter estimation. Yes.
Okay.
Mhm.
Yeah, if I can comment, I think Yongxin, the whole for the component understudy and the failure mode understudy, the assumption is that we have the knowledge of the whole life cycle, right? Of the behavior or the propagation. So I think that's the assumption here. So if we change to a different failure mode, we may need to look at a different physics domain model in order to fit it better, right? That's why Meryl mentioned the frictional entity. That's the failure mode we look at. The metric we look at with a colleague at Argonne. So if we get the opportunity, we'll look into that model, see how it works with the framework. The other thing is, I think your comment on the with lambda physics being 0. My comment is, Mario, maybe you can look at whether it's numerical 0 or it's actual 0. It appears there's a little bit of leak of the physics domain model information into the results. Otherwise, it wouldn't have behaved like that, right? If you go to slide 16, I think, the next. Yeah, the chart C here, the plot there, right? If you look at the 50% of data, if there's zero knowledge of the physics domain models, you wouldn't, I would agree with you. But my thought is whether the weight of being 0, is it only numerical? It's not actual. There's still kind of some kind of a level of data leak, right, in there.
Sometimes depend on
I
the
don't know.
underlying data-driven models, the nature, right? I think the neural network is non-linear. Sometimes they probably just naturally, regardless of how the data is going to be, they just kind of go like.
That could be the model itself.
Could be that way, yeah. If you use things like a Gaussian process, which is a linear interpolator, and usually they don't behave like that way. The spline is another one. Sometimes spline beyond the boundary, they kind of just go up, regardless of how the real data is going to be. Yeah. So
I'm gonna come back to you, Jung, with a better answer. I need to do a simulation because basically the data that we have, it's about A. Looking at this differential equation, we have data on A, while we will need to have data on N, because the N in this case is the solution of the differential equation. So we to perform the simulation, we did a pre-processing data where we will basically transform the data from A to N, doing certain interpolation, and we were using actually as a in the loss of the data, as data we were using data on N, not on A. So here, what we can see here is just the projection of the solution on this kind of graphics, on this kind of axis. So it's not the original one. I don't know if it's clear. I'm gonna send you more plots of the actual simulation to see how the neural network on the purely data-driven training will perform on the data of N rather than A. So probably we can have a better idea on how the behavior would have been.
that would help. Yes. Any other questions?
Yes, I just was wondering if this approach is, because it seems like a very indeed it's a regression-like problem, and I was wondering if other methods that are non-neural networks based, but I don't know, that's something simpler, a polynomial fit, or a spline, non-parametric.
Oh yes,
would suit and would speed up the process.
but you will still have to use the residual of the differential equation to give the.
Yeah, of course. I'm talking about physics-informed machine learning in general,
yes.
not physics-informed neural networks. but physics-informed machine learning, and instead of a neural network, I can do a spline there, and I can feed that in half a second, less than milliseconds.
Yes, you can definitely.
Yes.
Yes, definitely.
Yes, because I had an experience in wind, fitting a wind power curve, which is like a sigmoid.
Yeah.
And there were a lot of complexities with XGBoost and all that stuff. And in the end, I fitted an spline, and it was wow, wonderful.
Yeah. Yes,
Okay.
exactly.
Yeah.
That's
Yeah.
totally
Yeah.
possible.
Yes. Yes. It's interesting. Just to, grow in a very practical way.
Yeah.
Yeah.
If I remember correctly, I do an spline interpolation on the data. I don't remember I did it for this particular simulation, but many times I can do it. To avoid overfitting, basically.
Okay. Yeah. Free methods also, no, can it's interesting. It's the whole universe of
Yes.
things. Good. Yeah.
Mark, I see your hand.
Thanks. Thanks, Mario, for such an interesting presentation. I just have one question. So, to tackle the computational issue of solving PDE, you discussed that you make the neural network single layer. I'm wondering if for another type of fault detection, we had to use multiple inputs, multiple covariates, like not only just one dimensional. Could the computational issues of PDE be solved still with these tricks?
Yes. With our framework in our paper that you can find here on the bottom, we solved PDEs. This was back in the day, so we didn't optimize the framework very much to tackle more complex PDEs, like for example with the sharp gradients. What can be a Burger equation, for example. That's what we show in the paper, that it was one of the lack of the frameworks. But there are many colleagues of mine, especially from Purdue University. I can send you some papers later, where they perform high dimensional PDEs with sharp gradients, with good, very good accuracy in the solution and very short amount of time by tackling it with domain decomposition. So with domain decomposition, it's way easier because you decompose the problem in small problems. So your least square algorithm will not need to perform the inversion of a big matrix. By decomposing it, you have to perform the inversion of very small matrix, which is very easy and fast and even accurate. So to answer to your question, my answer is yes, you can do it. And for both forward modeling and also parameters estimation, inverse problems.
Thank you.
Thank you.
Well, I think that more or less conclude our today's presentation discussion. I'm very pleased to see we have a pretty thorough discussion after the presentation. That's great. So as Mario is going to send me the slide, I'm going to post the slide and the recording a little bit later on the WeDoWin platform, because right now actually Unreal is in the shutdown mode. And we try to not trigger anything which in contradiction to that. But those material will be posted. As advertisement for November, we're going to have Dr. Jian Tao from Texas A&M University talk about digital twin and the wind energy. So, but anyone in the audience, if you like to present something, share your thoughts, experience, and the project you are doing, let me know and send me an email, and we'll arrange you. So right now we have until January of 2026 being lined up, and then but the rest of the days are all kind of available. So with that, I wish you a good day or good evening, and I'll see you in a month. Thank you.
Thank you. Thank you, everyone.
Thank you very much.
Thank you, Mario, for the presentation and your time.
Thank you guys for participating, and feel free to reach